So Hermitian operators make eigenvalues interesting. So we are going to talk about the eigenvalue spectrum of Hermitian operators or self-adjoint operators. So at some point I will tell you what the difference between Hermitian and self-adjoint is. When we're dealing with final, but let me just give you a preview. When we're dealing with a finite dimensional Hilbert space, the two concepts are identical. But when we're dealing with infinite dimensional Hilbert space, we have to restrict the domain of the application operation of our operators to vectors where the inner product is converges, where the sum converges. And if you do that, then those operators are known as self-adjoint. But if you didn't do that, then in general they would be Hermitian. So self-adjoint is a more restrictive concept than Hermitian. So let's talk about the eigenvalue spectrum. And the statement that I want to make is, and I'll prove, is that the eigenvalues lambda m of the eigenvectors let's call them psi m of a Hermitian operator are real. Let's of a Hermitian operator, say A hat, are real. Okay, so this is a very important theorem that we are going to prove. Okay, the eigenvalues of a Hermitian operator are real. Okay, so here's the proof. So we are assuming A dagger is equal to A. That is, it's Hermitian. Now, A acting on its eigenvector psi m is giving me the same vector back, but up to a number lambda m. And this is the eigenvalue corresponding to this eigenvector. Now, we can take the conjugation of this, the dual of this, and the dual of this is going to be this equation. Okay? And so then what we say is that, so let's number this equation. So this is equation number 1. So this is equation number 2. Then from equation 1 and 2, what we get from equation 1, if we left multiply equation 1 with, say, psi m, the bra, let me just use the notation to clarify that, this is the, because, this thing is just this, right? And over here, this is just a number, so it lives outside. Okay. And from equation 2, if I do the same thing, but multiply with psi m ket, then I get, okay, so yeah, so we get a dagger, right? So we are multiplying equation 2 by psi m ket. But see that A is equal to a dagger. So that means that, let's call this, say, 3, and let's call this 4. That means that 4 can be rewritten as, so this is from 1, and this is from 2. 4 can be rewritten as psi m a, psi m, and psi star, there's an m here, lambda m star, psi m, psi m, and let's call it 5. So now from 3 and 5, if I subtract 5 from 3, the left-hand side is the same. So we get 0 on the left-hand side. The right-hand side, I get lambda m minus lambda m star, the bracket of psi m with itself. But we're assuming that psi m is not a zero vector. That means that even if it is not normalized, this is not equals to 0. So for this to be satisfied, we see that lambda m has to be equal to lambda m star. But lambda m is the eigenvalue, and therefore we see that it is a real eigenvalue. Okay, so any question about this proof?
No, sir.
Okay. So this is pretty easy, but it's a very, very interesting and very powerful proof. And